welcome everybody. My name is Florian Kleemiß. I am rather new in the Olexis field, and I developed a tool that is called NoSpherA2. NoSpherA2, non-spherical atoms in Olex2. Usually, if you measure a very high quality data set or something, what you see in the end is that you have residual densities in the bonds, right? And this is type of information that you completely omit if you use the independent atom model. The independent atom model is the spherical form factors that most people know from the international tables and that are widely used in routine refinement softwares. But as you can see in the measurement like this, we're basically missing information that we very well know about, and that in the charge density field, they tried to use this for quite some time already, but it was always quite difficult to actually use this type of information. And what I have tried to implement is in the first instance, the Hirschfeld atom refinement in Olex2 in a way that it's usable from the GUI and doesn't require so much additional input files and additional setup, but rather works from just the normal way you would refine your your measurement. And so in principle, NoSpherA2 is intended to not only be for people who want to do Hirschfeld atom refinement, but we might open this format. It's a standardized format. There's an archive article about the format that we are using to get the asphericity into Olex2. So in principle, this file format is open to use any kind of asphericity, but so far I've focused on implementing Hirschfeld atom refinement since I am a PhD student of Simon Grabowski in University of Bern. I know that one quite well. So what is Hirschfeld atom in the beginning? So maybe I can explain this very shortly. We know that we can calculate the quantum mechanical wave function of a molecule. For example, in a molecular compound like this, it's rather easy to imagine that we can easily calculate a molecular wave function and then use so-called Hirschfeld partitioning to cut out each individual atom of the electron density that we see from the wave function. So what we do is we use the Hirschfeld partitioning, which just asks how big is the contribution of my atom that I'm looking at to the whole molecular density from the wave function. Using this cutout criteria, basically we multiply the density of the wave function with this weighting scheme for each individual atom, and then we can cut out atoms in a fuzzy way. So it's not very rigid, it's diffuse atom shape, and this way we can describe additional features like bonding and polarization. And in this way we can obtain better scattering factors for each individual atom, which are tailor-made to that atom in that very specific position, and then use it to do our refinements. Open refine again, and if you use Olex2 refine, you can find NoSpherA2. And NoSpherA2, if you tick it, will give you a lot of options. So in the beginning, what it will say, please select. Please select means we need to select what type of input we want for our aspherical refinement. And at the moment, we have interfaces to different softwares to do wave function calculations. There is plenty out there. The, let's say, house code that is delivered with Olex2 is Tonto from Dylan Jayatilaka from Perth. That can do wave function calculations for you. PySCF is a code that is freely available and open source that you can just get by, for example, typing pip install PySCF on your computer if you have a Mac, for example. So it's easy to install and it's free. Everybody can get it without any restrictions. And the last and my favorite option is Orca, because it is very, very powerful. It's very, very fast and very efficient. But Orca you have to get from the Orca forum website. In the help of NoSpherA2, we have put links to different informations, and also here is a list. If you want to get Orca, you can click on this web button, and then it should open the browser for you to download Orca from the forum. But if you look for the Orca forum on your favorite search engine, you should also easily find and be able to register for Orca. Then you just install it, and in principle, the only thing you need to do is tell in settings, either through your system environment variable or through this path that is here in these settings in home of Olex2, you can give the path where Orca is installed, and then he will find it and give you as a suggestion in the drop-down menu. There is also an interface to Gaussian, let's say Gaussian 09, 16. But since Orca is my favorite option, at the moment, I can't guarantee that the Gaussian interface works 100% of the time. So if you, for example, select Orca, what you will have in the beginning is that the extras are not extended, and it selects some default settings for you. And in principle, what you can do is you just click refine, and then additional windows will appear. So maybe I have to change my screen share here a bit. I hope you can see now that a window popped up where I run the actual wave function calculation now. So what Olex does is it takes the molecule as it is on the screen, puts it into Orca, runs a quick calculation. You can see in the settings that are the default settings, it should be rather quick actually. And this wave function is then used from the NoSpherA2 program itself to analyze the density of this molecule. So it's making Becker grids to integrate the density, then it's calculating spherical densities because Hirschfeld partitioning is based on spherical densities, and afterwards it's calculating the wave function based aspherical densities to describe your molecule in the aspherical way. And now the only thing left is to calculate for each reflection in your reflection file the contribution of each atom to the scattering, so to the scattering factor. So you can imagine that for a high resolution measurement, you have quite some unique reflections. In this case, it's 40,000 reflections, 41,000 reflections, and I have 400,000 grid points. I'm sorry, this might take a few minutes in extreme cases. If the molecule gets bigger, the calculation becomes a bit more complicated. But in principle, this will then generate a file which contains all information needed for Olex2 to do the refinement in an aspherical way. So this is one step of Hirschfeld atom refinement. We have the generation of a wave function. We have the partitioning of the atoms inside this wave function. And then we have the refinement using this aspherical information. And what does it give us? You can see that Olex now switched all hydrogen atom parameters by default to be anisotropic. And in many independent atom models, this would be unreasonable. But the major benefit of Hirschfeld atom refinement is that we can also describe the hydrogen in a more sophisticated and more correct way. This means that we can describe the contribution to the bonding of this hydrogen atom more accurately than having the spherical scattering factor, and therefore obtain reasonable bond distances. You can see here that the bond distance for this carbon-hydrogen bond is far closer to what we would expect and what we know from neutron diffraction. And in this way, we can improve our refinement. So now I have this so-called TSC file. It's the tabulated scattering factors. And now I can use this over and over again to re-refine. So you can see, for example, this drastically changed the weighting scheme. Before I had an R value of 3.5, and now I'm already at 2.8 using a very quick and dirty calculation. As you can imagine, if there's theory and DFT involved, there's loads of different options you can select. So if I want to update this table of tabulated scattering factors, I have to click this button here to update the table. And then if I open the options, I can select all kinds of things I want to use for this calculation. So the first thing, if we have more sophisticated theoretical calculations, we will get more sophisticated tabulated scattering factors. If we, for example, change from a single valence basis set to a triple zeta basis set, we can improve the description of our molecule already quite significantly. And if we use PBE, for example, as a method, it's a quick and dirty GGA type DFT functional. If we want to use, for example, B3lib or MO62X, there's various functionals available. We can fine-tune our settings for the theoretical calculation to optimize. But in my experience, PBE is already quite good and it is very fast. So if you have a multi-core computer, you can use parallelism. The calculations in NoSpherA2 are fully parallelized. So if you have Orca installed, you need to install Orca in the parallel installation. This is rather tricky because it's a different file and it's on the bottom and it says, so Horst just informed me it became automatic. So you can install Orca, but you also on Windows need to install Microsoft MPI to enable parallelism on your computer. If you're using a Mac or if you're using a Linux computer, you have to install OpenMPI. So for Mac users, it will be through Homebrew. I would suggest that you can install OpenMPI. And on Linux, you just get the tarball from OpenMPI and just compile it yourself. And then if Olex at startup finds the proper setup of MPI executables, he will give you the option to run parallel calculations. If there's no MPI installed, he will just give you the option of one CPU. But it helps a lot. So it's very efficiently parallelized at the moment. So if you have more atoms than you have CPUs, you will linearly benefit from parallelism. If you have, let's say, only 3 atoms but 64 CPUs, maybe this will not help you so much. But at the moment, I think it should quite nicely scale. For the wave function calculation stuff, you also can define the amount of memory that you want to dedicate to this calculation. Because if you dedicate too little memory, the calculation might crash. If you dedicate too much memory and your system runs out of memory, this might actually freeze your computer. So I would suggest checking how much memory you have available at the moment. By default, if you open a new structure, he will check how much memory you have free at the moment and will use 75% of that. But this might change. And if I always change this according to what your computer does at the moment, this GUI would always auto-update. So I disabled this feature. One thing that you have to think about is charge and multiplicity. And from the test users, I heard that this is particularly tricky in some cases. So I try to explain what charge and multiplicity in this situation refer to. It is not the multiplicity from crystallography. It is the multiplicity from quantum mechanics. So if you have, for example, open shell system, or if you have a transition metal somewhere in your molecule, this defines whether it is a high spin or a low spin complex, whether you have unpaired electrons and how many of them you have. For example, if I would imagine a tetrahedral metal organic complex, For example, let's say from the examples, if I use this copper example, this is a tetrahedral copper between these nitrogen ligands. I would count the electrons on this atom, and I would come up with, let's say, 3 electrons in the d orbitals. And I know that in tetrahedral complexes, usually the high spin form is there. I know that these 3 electrons would be all same spin, or at least not paired. Then I can tell the software that this will be a multiplicity of 4. So the multiplicity is 2 times the spin plus 1. The spin of an electron is half. If I do 2 times the spin of 3 electrons, it will be 3, and it is plus 1, so the multiplicity is 4. If I put a multiplicity of 4, this calculation will then assume that we have 3 unpaired electrons somewhere in the molecule, and if quantum mechanics work the correct way, they should be located close to the copper atom. But let me switch back to the other molecule, where you can see that the multiplicity is actually 1 at the moment, because I assume that this is all paired electrons. This is more or less an organic molecule. Here I assume that everything is in the ground state. Another switch that you have is the integration accuracy. The integration accuracy is basically the question, how precisely do you want the NoSpherA2 to sample the electron density around each atom? So if you do this in a very low accuracy, the calculation will be very, very quick. But for, let's say, uncommon bonding situation, this might also lead to less precise results. So I would suggest normal is always fine. If you go high, your calculation will take a bit more longer. Max is basically the maximum settings in any software involved. This will, of course, take a bit longer. But if you want to benchmark how fast your computer is, or if you really don't need it for today, you can play with max. In Hirschfeld atom refinement, as it used to be, there was a restriction that there cannot be any atom that is heavier than krypton. This we overcame recently by including relativistic all-electron basis sets, that is the X2C family of basis sets. The X2C family of basis sets has relativistic contraction in the atomic orbital coefficients. So this way you can use a relativistic Hamiltonian in your wave function calculation. And this way we can now tackle atoms up to radon. If you have some really, really heavy uranium or something, we have to wait for theory to catch up with that, because we need all electrons. If you imagine that we do a Fourier transform of the electron density of your atom and there's effective core potentials, we cut out the electron density of your core, but the electron density of your core is actually quite important for the scattering of that atom. And if it's not there, you cannot describe the atom properly. So we need all electron basis sets, and this is why we have to stick with these X2C basis sets. If you watch closely, this relativistics button, it's the toggle switch which will allow or disallow the relativistic Hamiltonian in the calculation. If I go back to dev2 SVP, it will disable this automatically, but if you really, 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 really want to do it relativistics using the wrong basis set, you can also force him. I would not suggest that. But if you switch to X2C, he should automatically enable this. So if you are, let's say, only quickly starting a calculation, I hope he will catch a few of the errors that might happen. These last switches are basically convenience switches. So HANISO will just do what is on the screen. I can type select all hydrogen atoms, and I can type NS minus H. It will put anisotropic thermal displacement parameters on all atoms. If this is enabled, he will do it over and over again. So if you want to keep any atom isotropic, you should disable this, otherwise he will overwrite it again. The next one is no affix, because if you do H-at on an independent atom model structure, it's useful, it helps you, it puts atoms where they should be and they don't run away. But in this kind of refinement, we don't want to have a writing model where it is on 0.9 the hydrogen distance, but we want to freely refine the hydrogen atoms, all XYZ and all ADPs. Therefore, I put this, which will remove any affix command that is found in your hydrogen atoms. However, it might be or might prove useful that you can later on, if you, for example, have more difficult cases, you can put affix back in. So if you want to, for example, keep the angles between atoms fixed, but not the distances, you can use affix 22, for example, for a CH2 group. I might come to this point later. So then you need to disable this, but in the first calculation, why not try and see whether your data set can handle free refinements? And then here on the bottom, we have something that is called this kind of option changes if you switch between softwares. This is the software specific options, let's say. In Orca, there is, you can control how quickly the wave function and how precise the wave function should be calculated. So in this setting in Orca, we have a convergence threshold. The convergence threshold is basically how many digits need to be zero shift until we consider this wave function to be done. And the last option here is the convergence strategy, which is basically how much acceleration of convergence do we allow, how much damping do we put in. So in wave function calculation, there's various ways to make the wave function converge. And if you select here normal conv, this is the default settings that would be there if there is no further mentioning of anything in the input, but you can, for example, choose easy conv. If you know that the wave function calculation is very robust, this will save you at least 1 or 2 cycles, which might be useful if you use a very sophisticated method. Or if you have, for example, a transition metal with open spin system, where you experience problems in converging the wave function. When there's like 50, 40 cycles and it doesn't really converge, you can go to slow conv or even very slow conv to very, very carefully go into the minimum of the hyperpotential energy landscape. So this, in the Orca manual themselves, they recommend to use slow conv for metals, transition metals. And in our experience with this first implementation, I would always recommend using slow conv for transition metal complexes. And let's maybe put this to a test. So sucrose, if you have any experience with wave function calculations, you might say that sucrose is already quite a big thing to actually run the calculation on. And if we do the IAM, just to have the final IAM model, we see, okay, this is how we expect it to look. Actually, in this case, I have no affixes, I have no writing model. This is already refining hydrogen atoms freely, but I can now enable NoSpherA2. I select my wave function generator. I use default settings. Let's say he will save the settings. So if you changed something on the structure and open it again, he will load the settings that were there before. That's why I had some changes here. So the last option I did not speak about, I missed it, is this H button. So if you click refine now, what he will do is one calculation. I hope this will end in a foreseen time. Because this PBE functional is very, very efficient, the wave function calculation actually becomes doable on a laptop. I'm sitting on a laptop here. This is not a fancy 100-core machine or something. And then we just partition the density. Now we have the partition density. So for example, the table I print here, it has Beckett charges, spherical charges, and Hirschfeld charges. So these are, let's say, the charges that we obtain after applying the partitioning scheme. And this might be useful to spot, for example, an error. If you have the wrong multiplicity and the wave function tries to squeeze away some electrons somewhere where they shouldn't be, you can most likely see this in unreasonable charges somewhere. For example, some 10 times charged carbon atom or something. You should be worried if that happens. And most likely something is wrong in your wave function calculation. And as you can see now, I have sucrose refined here with all hydrogen atom ADPs looking more or less nicely. You can see that the resolution of this measurement on molybdenum is not extremely high, but it's sufficiently high to get some kind of information from this calculation. But the point is, the scattering factors of this TSC file were calculated for atoms that were sitting in the previous position of the IAM. But now I shifted them away. So if I now relax the density to fit this situation, I will get an even better description of my structure, and I will improve my ADPs again. And this is the last button that I didn't tell you about yet. If you tick this one, he will basically do the process over and over again. So he will do a wave function calculation, partition, refine, and now calculate a new wave function based on the geometry that you obtained after refinement. And the good thing about this is he will use the wave function that you calculated in the previous step as the initial guess for the new wave function calculation. So hopefully this will save you a lot of time and energy. And so if I do this now, he will use what is on the screen at the moment. Since I started it again, he does from scratch the wave function calculation at the moment. So you can watch delta E, the shift in energy. If that goes down and up and down and up and down, you might have to choose slow conv, but in this case it works. I've run sucrose a few times now, so I'm pretty sure it should work. Then we do the partitioning again. We just have to wait a few seconds. And then hopefully we will see how we iterate over the refinements and how it becomes quicker and quicker the closer we get to the final result, as we need less and less wave function calculation steps to obtain a reasonable wave function. So maybe this is then the time for you to go grab a coffee. If you're in your lab or something, this will buy you some time while your computer is doing the work for you. And now you see I'm starting Orca over and over again. And now you see that we have a different input. So he already has quite little change in energy because we used the guess from the previous calculation, and now it should converge quite quickly. And in the end, what it prints for you is a table where we see how the refinement converged over time. Because in the normal IAM, you have the table that you see here on the bottom. You have the shift over ESD, and this tells you how it is within within each least square step. But if you think about it now, each least square step becomes just one cycle in this iterative procedure of Hirschfeld atom refinement, where we calculate the TSC again. So what we do is we save the old geometry and ADPs, we save the new geometry and ADPs, and we compare how much shifted between the full least squares step. So it's a different kind of table in the end, which is basically the sum of all shifts in the least squares. And this way you have to think in two ways. You can have an unstable least squares in the worst case, or you can have an unstable Hirschfeld atom refinement, where the wave function, for example, is really not behaving nicely and jumping around. And then this is not a fault of Olex2 refine, but this is the fault then of the wave function calculation, for example. So you have to look in a different pace to solve this issue. So if we do it here now, hopefully it will finish at some point. There was a previous implementation of Hirschfeld atom refinement in Tonto, where the least squares was also handled by Tonto. But this implementation had some drawbacks. For example, the refinement of special positions in very high symmetric cases, for example, some cubic FM3 bar M space group or something where you have many special positions. The atoms were just moving off the special positions and then exploding the structure. And Olex2 refine is very good in handling these kinds of things because it is handled very well in the independent atom model, the standard spherical refinement already. And we can use this type of functionality now also in our aspherical refinement. So what you can do is you can use, for example, restraints, you can use constraints, you can use affixes, you can use all the normal things that there are in Olex2 refine to get control over your aspherical refinement now. And if you see now, I have the table on the bottom here. 0 is basically what we went in with. And there we had a wrong weighting scheme. So this is why the R factors look like this. And then we had some major shift still in X and ADPs. And then we converged nicely. And the threshold is for stopping the refinement that we have less than 0.01 parameter over ESD shift. This is when we stop refining in the aspherical refinement. This is, I think, also in agreement with, for example, multipole models or other softwares. And basically, this is how you would handle a nicely behaving structure. However, Horst showed you already that there is things like disorder handling in Olex2. And the great thing is we can also make use of the functionality that we have in Olex2 now also for aspherical refinements. So in this case, what I have here on the screen is this THPP molecule that you have in your examples in home. And here I already prepared, as in a good cooking show, I already prepared a TSC file, which we can use to refine this now. But I will show you the process, how I would do this if I start from solving it from scratch. But you see here that using this TSC file, we have the disorder group. I can show you here that we have part 1, which is the major part, which I can also describe anisotropically the hydrogen atoms. And we have part 2, which has occupancy of 0.12. So if you imagine we have 12% of one electron that is contributing to the hydrogen scattering power. This is really difficult to find from your scattering experiment. Therefore, I assume it's best to describe this hydrogen atom isotropically because there is just not enough scattering power of this poor hydrogen atom to contribute significantly to the overall scattering picture. But if you have very brilliant data, you might be able to observe this also anisotropically. In this case, I will just start from scratch, solve this. And then I see, okay, this should be nitrogen. I can do this anisotropically. Now I see that I have some hydrogens here, so I do Q2H. Okay, this one is maybe weird. Let's see. I will take this one away and make this one a hydrogen atom. And now I can maybe split this. Move this over here. So I have the second part. Okay, the hydrogen atoms go haywire. Well, it's sort of expected if you consider what I said previously. So why not add them with constraints? He didn't recognize that it is CO2, CH2. So I will go to tools, hydrogen atoms, and make this CH2. This is CH2. Also give an isotropic motion. And now the question might arise, how do we handle this now? Because if we calculate a wave function for the two atoms being this close together, the wave function will be unreasonable. So what we do internally is we calculate two wave functions. One wave function contains only part one and part altogether. So basically what you see if you click this button, this will be our first wave function. And this will be our second wave function. And then we make a TSC file which contains both wave aspherical scattering factors. So if I now turn on NoSpherA2, I will show you both. If I turn on NoSpherA2 and I tell him to update the table, I select the settings. I assume it's a closed shell system. And for now, I want to keep atoms as they are. And I also want to keep the affixes for now. Let's see how it goes. Then I dedicate some more CPUs so you don't have to wait that long.
You want the H on?
No, I want the H off for now. Thank you. Select a quicker basis set, but in principle, you can also use TZVPP. It will not take too long if you use PBE. And then I run this refinement. So now I have the first wave function calculation. Which goes through rather quickly because it's not too many atoms at the moment. We do the partitioning. Luckily, we have a long cell axis, rather long cell axis of 14 angstroms, so there's enough data in here. This is the first half of the molecule. Now we run the second half. And then Olex2 will merge together both information files and create the total information we need for this refinement, which hopefully will then give us nice carbon-hydrogen bond distance and featureless residual density. I haven't shown you residual density yet. I should do that. So now you can watch on screen how the hydrogen atoms get further away and how the ADPs expanded in this case a little bit. And now we have reasonable distance for a carbon-hydrogen distance. So what you see now is the residual density is gone. I can reduce the level a bit. So you see it's static noise. And this is what you hope to see after Hirschfeld atom refinement. In an independent atom model, you would always expect to see residual density located on lone pairs, on bonds. But using Hirschfeld atom refinement or aspherical methods, you get all this information in your model. So you hope to see no residual density on the bonds, because I can show you what is different. I can show the so-called deformation density. And this is the difference between your spherical and your aspherical model. So this is actually where we changed something. And if you look at this map here, we have density in the bonds. We put it there in contrast to the independent atom model. And if I reduce the ISO value now, we can even see that, for example, in the independent atom model, there was more density here than there is now, because we took it away from the center of the ring and we described the bonding. In overall sum, the deformation density of a good model should be 0. And I can tell you where the biggest contribution is. It is inside the atom core. So we take away electron density from the core and describe the bonding. And this way, you can even see, if I go to higher ISO value, for example, this hydrogen atom, if I would describe it spherically, it would have a sphere of density around its position. But now we take away density from where the bond is not, and we put it where the bond is. So we can describe the bonding better. And this way you can look what changed in contrast to your spherical refinement and why your residual density is gone. So if you had a perfect experiment without any experimental error, the deformation density and the residual density map before Hirschfeld atom refinement should almost look identical, because this is what you describe with the better assumptions that we make. Okay, I've been talking for 45 minutes now, I just see. Let's make this more interactive.
Hello.
Hello.
Hello. Yeah, I mean, it's so basic. It's nothing to do with this actually, but I noticed Florian go into a very nice tool where he could add the hydrogens, and effectively you could visually put in the different hfix commands for CH2, etc. I missed what he did because that's something I need to know just at a very basic level.
How to add the
it's on tools. I see.
Tools?
Yeah.
Hydrogen atoms, and then you can select if you want to have sp3, sp2, so the CH sp3 hybridized or CH sp2 hybridized. OH is there, or you can use whatever hfix you want.
Okay, so that's brilliant. Thank you. Hopefully that warms people up and you get some more advanced questions now.
Maybe this is also quite a new world. If you encounter any problems, if you encounter any questions, also you can just ask questions. You can write me, for example, at florian@olexis.org. And
there's a question.
There's a question. Is it possible to send the actual job to a powerful cluster and import the results back to Olex? As I show you, if you use PBE, I hope it's not necessary to use a powerful cluster anymore, but I can show you where the magic happens, basically. So if you set up a calculation, what will happen in your folder? I just clicked on the folder icon on the top here. There's the Olex2 folder. Inside the Olex2 folder, there is many things going on in NoSpherA2. So I have a NoSpherA2 history. The NoSpherA2 history will contain, whenever you do a calculation, the TSC files, wave function files, if there's any, and there's the WFN job. And the WFN job, for each part, he will back up all wave functions. So if you run it over and over again, like I do, you can very efficiently fill your hard drive. And there will be the input. In this case, I have input for the THPP. And this is the input file that you can, as it is, submit to a cluster, for example. And then if you do that and you tick update table, you should in principle let's not take a disordered structure because there it's more complicated. If you have, for example, sucrose, you can put the wave function as it is in the folder of your job. If it finds the wave function file in that folder, it will give you the option to just calculate it from that wave function file, and then use this to do only the partitioning on your computer then, not the wave function calculation itself. Yeah, so this is how you could just take the input file that Olex2 generated for you, but we don't have any interface yet to send the calculation to a cluster or something automatically. This is, so what Pilar, what exactly do you mean by spherically described atoms using non-spherical scattering factors? So what we do is we use the ADPs, the thermal motion, the positions, and use the non-spherical scattering factors because the thermal motion is used in a convolution later on to convolute the static density that you also obtain from spherical model, for example, from the international tables, and then get the full calculated structure factor that you refine, use to refine your model in the same way, because the mathematics behind it is the same if you use the spherical or aspherical static electron density. Okay, good. Lucas asked, can we add more basis sets manually? In principle, you can. So what you would have to do is you would go to where you installed Olex2. In my case, I have some Olex2 folder here, and there's the basis sets folder. In this folder, there is the basis sets that will be used for the calculation. And if you add an additional basis set file here, it will be found by the drop-down menu. However, these basis sets are in a special format, so you would have to go through the trouble of reformatting everything according to your needs, which takes some time if you want to do it for all atoms. Therefore, we have these predefined basis sets, and for them, I am, let's say, 95% sure that they are correct and they will work. If you put your own basis set, we cannot guarantee that the file format is correct, that all brackets are there, so you will have to go on your own adventure with that. Then Andreas asked, great talk, when do you think this tool will be published? I will go into lockdown most likely after I've been here to England, so I can start working on that. I hope we can finish the manuscript, let's say next month. So all calculations or validation are done. The manuscript needs to be written, and then hopefully we can publish it soon. That the plan was that in the IUCR meeting in Prague, we will have a session, a software session, where I will present this on an even a bigger base, I hope. Let's see what the current worldwide status does to this plan. But yes, so the plan is to get this out as soon as possible for me. Okay, what should I keep in mind by uploading the WFN file in AIM-all? You can use the WFN file that I generate in this procedure to analyze, for example, beta charges or bond critical points or whatever you like. So you can just use it as it is. If you have a converged model, if it didn't change in the end, so if you tick tar and it finished, you can use this WFN file to do any analysis you like. Georg asked, what are the signs that you have reach the limits of your data, it means that it is not reasonable to use a spherical model. In principle, if you use the same kind of parameters, so if you don't include the anisotropic motion on the hydrogen atoms, the number of parameters is the same as in the IAM. There is no parameters because I know that charge density people know from multipole model, the introduction of many more parameters introduces more problems. But since we say the scattering factor is fixed as it is from the wave function, we have no additional parameters in the least square step. So I would say as long as your model behaves reasonable, you can try to use the aspherical model. There have been tests that say you can do Hirschfeld atom nicely with 0.8 angstrom resolution data. Everything else is, I personally would say, but maybe Simon Grabowski can also comment on that, that you can use the aspherical model as long as the results give reasonable structures. Okay, so Simon just said, if you don't see residual density in bonds and lone pairs, how will not help much? Is multiplicity for more than one metal? The formula should be 2s plus 1n. With multi-atom centers, you have to, I would say you have to play around a bit, because there the situation might be so complex that you cannot just draw it on the paper, the MO diagram, and guess multiplicity correctly. So you can run various models and see whether the wave function converges, whether the results get better. So in principle, you would have to play around with that. From my point of view, but this is maybe a bit naive, I would say just select what suits your data best. And then try to argue whether this makes sense in the aftermath. So you look at the multiplicity that makes a good result, and then you try to understand whether this suits your metal situation. But in principle, you can also try to think about a construction approach where you can think about it rationally and then try to choose the correct multiplicity. But if there's like 4 or 5 metal atoms, I have to admit I would also be lost. Is there a resolution limit? I mean, what data do you need to use this kind of refinement? I think I commented on this already. If you don't, or Simon Grabowski actually said it very nicely, if you don't see any residual density or lone pairs, you might not see much improvement using Hirschfeld atom refinement. However, I tend to say, give it a try and see what it does.